Welcome back to Chapter 4, Part 2, Effects of Electric Current. And today we are going to study the heating power of electric current. I'm sure you must have noticed that when you use your laptop for a long time, or if you keep your mobiles for charging, the charger gets heated, the laptop gets heated, the mobile gets heated. Okay, so that means there is something that is happening in these gadgets, and so our instruments are getting heated up. And the longer you use your laptops or your mobile chargers, the more it gets heated up. So what is this power of heating produced by electric current? We know that what is electric current? It's the flow of electrons. And as electrons are moving, they are dashing against each other. They are moving in one direction. And the more the collisions, the more will be the heat that is produced due to electric current. Okay, now is it good to get our mobile chargers heated or our laptops heated? No, we don't like it. In fact, the laptops have got a fan inside to keep it cool. Okay, the reason is because that heat is wasted. Okay, but what if we use this heating power of electric current to cook something, or to iron our clothes, or to heat water in the water heaters, in the form of water heaters, or in the form of this electric iron for heating water? Okay, so then there we are making use of this particular property of electric current, which is called as a heating power. Okay, so electrical equipments like water boilers, electric cookers, then electric bulbs, they all make use of this heating effect of electric current. Moreover, do we use the same type of conductor, the same type of wire in all the gadgets? No. Some require a thin wire. For example, in bulb, we use a tungsten wire. Okay, that wire, tungsten, is getting heated and it glows. In case of, you see the coil here, which is used for heating the electrical rod that we call it to heat water. Okay, they use a different type of metal, a different type of conductor. The nichrome coil is used here in electrical cookers. Now, why do we use different types of conductors in different gadgets? That is what also we will try to understand. Okay, so before we understand that, let us understand this heating power of electric current was noticed by Joules, and therefore it's called as the Joules law of heating. So let's understand this Joules law of heating first. Now we know that when a resistor could be a bulb, it can be a wire, it can be a coil, okay, of conducting wire. When it is connected in an electrical circuit, heat is produced. It gets heated up due to the electric current. Okay, this is the heating effect of electric current. According to Joules, he calculated how this heat is produced. Okay, so the formula we use to calculate heat and to derive Joules law, heat is equal to the power into the time. As we know, longer we use electric current, longer we use the power, the more it will get heated. If I use a bulb or a laptop for an hour, 60 minutes, okay, it will get heated. If I use it for double the time, 2 minutes, okay, that is 120 minutes, that is 2 hours, okay, then it will get heated more because more power is used in 2 hours. So heat is equal to the power into the time that I used, but we have studied power is equal to the voltage, that is potential difference, into current I. And therefore you can get another equation, heat is equal to the potential difference into current into T, that is V into I into T. So this is one equation. Now according to Ohm's law, we know V is equal to I into R, that is current into resistance that is offered. Now replacing V in that equation 1, V is equal to I into T, replacing this V by I into R, we get the equation heat that is generated in the conductor is equal to I into R into I into T. This I into T is here. Okay, that means it is equal to I square into R into T, and this is considered as Joules law of heating. So what is what did he notice about heating power of electric current? He noticed that heat is directly proportionate to the square of the current. It is directly proportionate to the resistance that is offered, and it is also directly proportionate to the time. So therefore, according to Joules' law, heat generated is directly proportionate to the square of electric current, to resistance and time. Okay, the more the resistance, the more will be the heat that is generated. Okay, and the lesser the resistance, lesser will be the heat that is generated. Same with time, more the time, more the heat that is generated. More the electric current, more is the heat that is generated. Okay, so that's called as Joule's law of heating. Now you have a good reason as question 7. In electrical equipments producing heat, okay, iron, electrical heaters, boilers, toasters, an alloy of nichrome is used. As I mentioned earlier, we don't use, different gadgets use different conductors, okay, or different resistors. Okay, so here we use nichrome wire. We don't use pure metals. What is the reason? You can think about it. Pure metals will have a low melting point and they will boil, they will melt easily. We don't want electrical equipments to get heated as you are ironing your clothes, and here your along with the clothes being ironed, your electrical heater is, your electrical iron is getting melted. Okay, that's not going to help. So therefore we need to use different gadgets, or rather different resistors or different conductors in different equipment. Same with the rod for heating water. Okay, we use nichrome wire in the electric cookers. We use, or electrical stoves, we use more of these nichrome wires. The reason is nichrome wire is an alloy which is made of nickel and chromium. Now it is used as a heating element because of its high melting point. So even if a lot of electricity passes through it, a lot of current passes to it, okay, heating is equal to the square of electric current, that is I square, into the resistance, into the time. Okay, so therefore the melting point of nichrome is very high. It has low conductivity and very high, that is very high resistivity. It does not allow the electric current to pass easily, and more the resistance, more is the heat that is generated, and we want more of heat to be generated in these particular gadgets. Therefore having a high melting point does not allow the nichrome wire to melt easily when large amount of heat is produced, when large amount of current passes through it, and it does not melt, or neither does it get oxidized like the pure metals. And also it allows a lot of resistance, and therefore we use nichrome wires in these gadgets. Okay, so these are some of the different types of wires or conductors that are used, or resistors that are used for heating purposes. Tungsten filament is normally used in a bulb. Then you have these coiled filaments, okay, which will generate more heat. Then talking about the electric bulbs, I told you tungsten wire is used in electric bulb. Okay, now electric bulb has inert gas or argon, which is 85% with 15% of nitrogen filled in it. At the center of the lamp is that tungsten filament. Here what you see is a tungsten filament. Okay, now electricity will heat this filament up to about 2500 degrees, okay, Celsius, which is very high. Now tungsten has a very high melting point, so it will not melt at this point. Light output will be 18 to 15 lumens per watt. Operating life will be about 1000 hours. Efficiency is increased because of this coiling. The coiled filament will increase the efficiency of this bulb. Okay, so you have a question again. Tungsten metal is used to make a solenoid type of coil in an electric bulb. Solenoid is a coiled electric wire. Okay, we'll study solenoid as we study the lesson. An electric bulb uses the principle of heating effect of electric current. As electric current passes through the solenoid type of coil in a bulb, it gets heated up, and because of that heating up, it starts glowing, and as it glows, it emits light. Okay, so as the melting point of tungsten is very high, 3380 degrees Celsius. Therefore, it does not melt in spite of the tremendous heat that is produced. And we do not want the tungsten wire to melt in the bulb. Okay, then in practice, the units that are used for measuring electrical energy or to measure electricity. Okay, in practice, the unit kilowatt hours. This is the unit which is used. It's a bigger unit for measuring electrical energy rather than joules or watts. Now, power is the rate at which work is done. This is what we did in standard 9. Power is the rate at which the work is done, that is work upon time. The SI unit of work is joules and time is seconds. So therefore, the unit for power is joules per second. This joules per second can also be called as watt after the scientist James Watt. This unit of electric power is very, very small. Watts is very, very small electric current, and therefore for household measurements we use a bigger unit called as kilowatt hours or kilowatt. Okay, so when 1 kilowatt is used for 1 hour, we call it as 1 kilowatt hour. Now 1 kilowatt is equal to 1000 watts, just as 1 kilogram is equal to 1000 grams. Okay, so 1 kilowatt is equal to 1000 watts. In practice, 1 kilowatt energy or power is used for 1 hour, then we call it as 1 kilowatt hour. And 1 kilowatt hour is equal to 1000 watts into 1 hour. 1 hour means 3600 seconds. Therefore, you can convert this into 10 to the power 6. Okay, so 3.68 into 10 to the power 6 watt seconds or joules. Now 1 kilowatt hour is equal to 1 unit. We normally get our bills in units, 20 units, 40 units, 100 units, 300 units of electricity that we have consumed. Okay, so in this case we use units. 1 unit is equal to 1 kilowatt used for 1 hour. So in the next video I will discuss about what is short circuits. Okay, so keep tuned. We will meet again. Take care. God bless.